Hi and welcome to this final video in this acid and alkali series. In this final clip we're going to look at acid and base titrations, again as we've done in so many of these so far, and we're going to look at the titration curve that we have used previously as a way of generating values during a titration, or by a method to calculate the pKa of a weak acid. Now the important part of this is this inflection point here and what we would have known as the endpoint or as the equivalence point for a titration. And this is whereby we have a vertical section of the curve showing a rapid change in pH around the endpoint. So if this were for a strong acid, so something that started life at around pH 1, something like that, and we titrated that against a strong alkali or a strong base, something with a pH of say pH 14, then we would realistically expect a possible neutralization pH, endpoint pH of about pH 7. That wouldn't be too unexpected. Now, when we have titrated these also against a weaker acid, we have seen that the pH starts a little bit higher off. We then enter the buffer region, whereby we've got these larger concentrations of acid relative to base concentrations, as we looked at in the previous examples of buffers. And we may therefore expect, if we did the same titration against a strong base, so we finish at a higher pH there, then we may expect to see that the equivalence point pH may be slightly higher than 7, and it may not be unexpected to see it in the 8 to 9 region, whereby we've got a higher pH at equivalence compared to a strong acid versus a strong base titration. Now, if we are using a pH meter, then obviously we can use the numerical data to establish where the endpoint is. But many of you will have done a titration whereby you have an indicator which helps you visualize this endpoint. And a choice of indicator is very important. Now, an indicator is actually an acid-alkali, acid-base equilibrium in itself, and it will have its own corresponding pKa value depending on the indicator you're using. Now, methyl orange has a pKa value about 3.5, so its pKa is going to be somewhere in this region here. This means that its pH curve is going to follow a trajectory which is going to be different to the pH curve of the titration we are wanting to do. In real terms, what that means is that the indicator we are using has a pH range whereby it will rapidly change pH. For methyl orange, that's typically between about 3 and 4.5 pH units. So it will have this change range in this approximate region. If we were to compare that with phenolphthalein, it has a pH range of between about 8 and 9, going almost up to 10. But importantly for this, it has a different pH range under which it will operate. So phenolphthalein will be up here, and our methyl orange will be down the bottom here. And so what we need to do is choose an indicator which allows for our curve that we are looking for to change pH rapidly and go from one side of the band change for the indicator. So if we were to look at our strong acid and our strong base titration, which was this black curve that we had originally, this one here, we can see that as the pH changes, it slowly increases. Then we get the rapid pH change from about here to about here. Both of those pH changes would traverse each of the bands for methyl orange and phenolphthalein, depending on the concentrations we're using, obviously. And so for a strong acid versus a strong base titration, we could theoretically use either of these indicators. However, if we were to then look at the weak acid, we can see that its pH started at just under pH 3, give or take a bit, and its pH started to progress up the curve, which is essentially contained within the methyl orange switching region. This is going to get quite confusing because it's not going to know on which side of the band to lie. So methyl orange isn't going to be a suitable indicator. Sometimes it may look as though it's changed, sometimes it may not have done. But if we continue with the pH change of the weak acid versus strong base titration, it will perfectly cross the phenolphthalein during its equivalence change, meaning that for a weak acid versus a strong base titration, it's probably better to choose phenolphthalein. This is because when we sketch the titration curve, we can definitely see that a certain indicator is much more appropriate for certain titrations, whereby, as we said, its colour change range is falling entirely within the vertical part of the titration. Methyl orange and phenolphthalein are two very common ones, and as we say here, for phenolphthalein, you would want to be using a weak acid versus a strong base. For methyl orange, we could go the other way and use a strong acid versus a weak base. For strong versus strong, we could probably use either, but it's often a good practical skill to know which indicator is used if you've got a possible differentiation between the two that you'll be given. For most questions that we see commonly at examinations, most of them use weak acids versus strong base, so phenolphthalein is quite often the indicator of choice. It's got a nicer colour change in that it goes from colourless to pink and vice versa, so it's easier to see that endpoint as well, but just be aware of different questions which may turn up where methyl orange is the correct indicator for those ones. So thank you very much for this series of acid-base chemistry, and I will see you in the next series along.